Far beyond the reach of the naked eye, nearly 5.7 billion light-years from Earth, something extraordinary is happening in the darkness of deep space. At the center of one of the most massive galaxy clusters ever discovered lies a black hole so enormous that it challenges everything astronomers thought they understood about the universe. Its name is PhoenixA, and if current scientific estimates are correct, it may contain a mass approaching 100 billion times that of our Sun. To understand how extreme that is, consider the black hole at the center of our own Milky Way galaxy, Sagittarius A*, which contains about 4 million solar masses. PhoenixA could be tens of thousands of times more massive, placing it in a category so rare that scientists had to create a new term for objects like it: ultramassive black holes. These are not simply larger versions of ordinary black holes, they exist on a scale so immense that the laws of black hole growth begin to look incomplete. The story of PhoenixA began in Antarctica, where scientists using the South Pole Telescope were studying the oldest light in the universe, the cosmic microwave background, the faint afterglow left behind by the Big Bang. Hidden inside that ancient radiation, researchers noticed a strange distortion, a subtle signal caused by an enormous concentration of hot gas bending the energy passing through it. Follow-up observations using X-ray telescopes, radio observatories, and optical instruments revealed one of the most extreme galaxy clusters ever discovered, later named the Phoenix Cluster. This cluster contains thousands of galaxies and has a total mass estimated at nearly 2 quadrillion suns. But the cluster itself wasn't the biggest discovery. At its center, inside a giant elliptical galaxy, astronomers found evidence of an object whose gravitational influence was almost beyond comprehension, a black hole so massive it seemed to break the normal rules of cosmic evolution. What makes PhoenixA so fascinating is not just its mass, but its size. Black holes grow in direct proportion to their mass, meaning the larger the mass, the larger the event horizon, the point beyond which nothing, not even light, can escape. If PhoenixA truly contains close to 100 billion solar masses, its event horizon could stretch hundreds of billions of miles across. Light itself, moving at nearly 186,000 miles per second, would take weeks just to travel from one side of the black hole to the other. This isn't the kind of black hole most people imagine. It isn't a tiny point in space or a destructive cosmic vacuum cleaner. It's more like a gravitational territory, a region of spacetime so vast that it resembles a small star system more than an object. Crossing its event horizon wouldn't necessarily feel violent. In fact, because of its enormous size, the tidal forces at the edge could be surprisingly gentle. A person falling into PhoenixA might cross the point of no return without feeling anything unusual at all, unaware that escape had already become impossible. The greatest mystery surrounding PhoenixA is how something this massive could exist in the first place. According to standard models of black hole formation, black holes begin as the collapsed remnants of massive stars. Over billions of years, they grow by consuming gas, dust, stars, and by merging with other black holes during galaxy collisions. But PhoenixA may simply be too large for that explanation alone. To reach a mass of 100 billion suns through ordinary accretion, a black hole would need to feed almost continuously for nearly the entire age of the universe. In reality, black holes don't feed constantly. They go through active periods and dormant phases, sometimes blasting away surrounding matter with powerful radiation and slowing their own growth. That means PhoenixA may have formed in a way we still don't fully understand. Some astronomers believe it may have started as a direct collapse black hole in the early universe, forming not from a dying star but from the collapse of an enormous cloud of primordial gas. Others suggest repeated mergers between multiple supermassive black holes inside dense galaxy environments may have created something far larger than expected. What makes PhoenixA even more remarkable is that it appears to be active right now. Most ultramassive black holes are thought to spend much of their existence dormant, sitting silently at the centers of galaxies after exhausting nearby fuel supplies. PhoenixA seems different. The galaxy cluster surrounding it is filled with incredibly hot plasma, gas heated to tens of millions of degrees, glowing brightly in X-rays. Normally, the central black hole in a galaxy cluster acts like a thermostat. As gas cools and begins falling inward, the black hole feeds and launches powerful jets of energy outward, reheating the gas and preventing too much matter from collapsing into the center. This creates a balance. But in the Phoenix cluster, that balance appears to be failing. Cooling gas is pouring toward the center faster than PhoenixA's jets can push it back, triggering one of the most intense feeding events astronomers have ever observed. The consequences are extraordinary. The central galaxy of the Phoenix cluster is currently forming stars at a rate of nearly 1,000 solar masses per year. By comparison, the Milky Way forms roughly 1 solar mass worth of stars annually. That means PhoenixA's central galaxy is creating stars nearly 1,000 times faster than our own. Entire generations of stars are being born in cosmic waves, flooding the galaxy with light, heat, and heavy elements. Meanwhile, PhoenixA continues consuming the surrounding matter, launching jets of high-energy particles at nearly the speed of light. These jets carve giant cavities in the surrounding plasma, bubbles so large they could contain entire galaxies. And yet, even with all that power, the inflow continues. It's as if the black hole has awakened to find more fuel than it can control. PhoenixA may be giving us something incredibly rare, a live view of processes that were common in the early universe, when the first supermassive black holes were rapidly assembling. It's possible we are watching a cosmic event that shaped the earliest galaxies billions of years ago, now replaying itself in a distant corner of space. And perhaps most unsettling of all is what PhoenixA suggests about the wider universe. If one ultramassive black hole exists, there may be many more, silent, dark, and invisible to our telescopes because they are no longer feeding. Hidden across billions of galaxies could be gravitational giants larger than anything we've yet discovered, quietly shaping the evolution of stars, galaxies, and clusters without us ever knowing they're there. PhoenixA reminds us that every time humanity believes it understands the limits of nature, the universe reveals something bigger, stranger, and more extreme. Somewhere in the darkness, far beyond the stars we can see, this enormous black hole continues doing what it has done for billions of years, feeding, growing, and waiting. And long after Earth, the Sun, and perhaps even humanity itself are gone, PhoenixA may still be there, silent in the dark, impossibly massive, and still hungry. As astronomers continued studying PhoenixA, the deeper they looked, the stranger the system became. The black hole itself was only one piece of a much larger and more violent environment. Surrounding PhoenixA is the Phoenix cluster, an enormous collection of galaxies held together by gravity, but between those galaxies lies something equally important, an ocean of superheated plasma. This plasma fills the empty-looking space between galaxies and reaches temperatures of tens of millions of degrees, hot enough to shine intensely in X-ray wavelengths. Most galaxy clusters contain this kind of gas, but in the Phoenix cluster, the amount of energy being released is extreme. Observatories like NASA's Chandra X-ray Observatory detected an X-ray brightness so intense that Phoenix quickly became one of the most luminous galaxy clusters ever observed. It wasn't just massive. It was alive with energy. Under normal circumstances, this hot gas should slowly cool over time. As it cools, gravity pulls it inward toward the cluster center, where it can collapse into clouds and begin forming new stars. But in most galaxy clusters, that process is interrupted by the central black hole. As matter falls toward the black hole, it releases enormous amounts of energy in the form of radiation and high-speed jets. Those jets blast back into the surrounding gas, reheating it and preventing too much cooling. This creates a cosmic balance, a self-regulating system where the black hole acts almost like a thermostat, controlling how much gas reaches the center. For years, astronomers believed this feedback process explained why many giant galaxies stopped forming stars long ago. But Phoenix changed that picture completely. In the Phoenix cluster, the cooling gas appears to be overwhelming the black hole's ability to regulate it. Instead of a stable balance, astronomers are seeing a runaway cooling flow, vast amounts of gas collapsing inward faster than PhoenixA can push it away. The result is one of the most intense star-forming regions ever discovered in a massive galaxy cluster. At the center of Phoenix, stars are being born at rates that seem almost impossible. Massive blue stars, some dozens of times heavier than our Sun, are forming in enormous clusters. Entire stellar populations are emerging in regions where, according to older models, star formation should have nearly stopped billions of years ago. This central galaxy is essentially experiencing a rebirth, building stars at a rate few galaxies in the modern universe can match. At the same time, PhoenixA is far from passive. As matter spirals inward toward the event horizon, it forms an accretion disk, a swirling disk of superheated gas and dust orbiting at tremendous speeds. Friction within that disk heats the material to millions of degrees, causing it to radiate enormous amounts of energy across the electromagnetic spectrum. Some of this energy escapes as light, X-rays, and gamma rays, while another portion is redirected into the powerful jets emerging from the black hole's poles. These jets travel at close to the speed of light and carry enough energy to reshape the structure of the entire cluster. As they punch through surrounding gas, they create giant cavities, regions where the plasma has been pushed aside by the force of the outflow. Some of these cavities are so enormous that our own galaxy could fit inside them multiple times. But despite all this power, PhoenixA may still be losing the battle. That's what makes this system so scientifically important. It appears we may be witnessing a black hole operating at incredible energy levels while still failing to fully control the environment around it. This suggests there may be limits to black hole feedback that we didn't fully appreciate before. For decades, black holes were seen as the ultimate regulators of galaxy growth, capable of shutting down star formation by heating and ejecting gas. PhoenixA hints that under the right conditions, even one of the most massive black holes in the universe may not be able to keep up. This raises deeper questions about the early universe. Billions of years ago, when the first galaxies were forming, the cosmos was richer in gas, collisions were more common, and black holes were growing rapidly. Some astronomers now believe that systems like Phoenix may be giving us a glimpse into what those ancient environments looked like. In other words, PhoenixA might not just be an unusual object, it could be a living fossil, preserving physical processes that shaped the first generation of galaxies. By studying it, scientists may be learning how the earliest supermassive black holes formed, how they grew so quickly, and how they influenced the structure of the universe itself. And yet, one mystery remains even more unsettling. If PhoenixA exists, and if it has reached such an extreme size, then it may not be alone. Somewhere in the darkness beyond our current surveys, there may be other ultramassive black holes, larger, older, perhaps even more active, hidden inside distant clusters we haven't fully mapped yet. Some may be silent, having consumed all nearby fuel billions of years ago. Others may still be feeding, invisible except for the effects they have on surrounding galaxies. Every new observation of Phoenix seems to suggest the same thing: the universe may contain structures far larger and more powerful than we once imagined, and we may have only just begun to find them. As the evidence surrounding PhoenixA continued to grow, astronomers began asking an even more profound question: not just how this black hole formed, but what happens when an object this massive continues to grow for billions of years. Black holes are already among the most extreme objects in the universe, but ultramassive black holes like PhoenixA exist at scales where our intuition completely fails. Their gravity doesn't just influence nearby stars or even their host galaxies. Objects of this size can shape the evolution of entire galaxy clusters, affecting the motion of thousands of galaxies and the distribution of hot gas spread across millions of light-years. In a very real sense, PhoenixA may not simply live inside the Phoenix cluster. It may help define what the cluster becomes. To understand that influence, imagine a structure so massive that its gravity helps control the movement of matter across distances that would take light millions of years to cross. As galaxies orbit within the Phoenix cluster, their motion is shaped by the combined gravity of dark matter, hot gas, stars, and the central mass concentration surrounding PhoenixA. Over cosmic time, smaller galaxies can fall inward, collide, and merge with the giant central galaxy. Every merger delivers new stars, new gas, and sometimes even new black holes. This means PhoenixA may still be growing not only by feeding on gas, but by absorbing the remnants of entire galactic collisions. Each merger adds more mass, more momentum, and more energy to an already unimaginable system. Some theoretical models suggest there may be an upper limit to how large black holes can become. As a black hole feeds, the material falling inward becomes so hot and energetic that it begins pushing outward with radiation pressure. Eventually, this outward energy can become strong enough to blow away surrounding gas, cutting off the black hole's own food supply. This natural balance is known as the Eddington limit, and for decades it was thought to place a practical cap on black hole growth. But PhoenixA may be challenging that assumption. If its mass estimates are accurate, then either it found ways to feed beyond what we thought was possible, or it grew through periods of extreme efficiency unlike anything we've directly observed before. Either possibility forces astronomers to reconsider how black holes interact with matter under extreme conditions. Even more fascinating is the role of dark matter in systems like Phoenix. Dark matter makes up most of the mass in galaxy clusters, yet it cannot be seen directly. Scientists only know it exists because of its gravitational effects. The Phoenix cluster is believed to sit inside a colossal dark matter halo, an invisible structure helping hold everything together. That halo may have played a major role in PhoenixA's growth. By creating a deep gravitational well, dark matter could have trapped enormous amounts of gas in the cluster's center for billions of years, providing PhoenixA with an almost endless reservoir of fuel. If that's true, then ultramassive black holes may not simply be products of their galaxies, they may be products of the invisible dark matter scaffolding that shapes the large-scale structure of the universe. There's also another possibility that pushes the boundaries of modern physics. Some researchers have speculated that black holes of this size may eventually enter a category known as stupendously large black holes, objects so massive that they approach theoretical limits predicted by general relativity. At these scales, the event horizon becomes so large and the surrounding gravitational influence so complex that new physical effects may begin to emerge. While Einstein's equations still describe these objects remarkably well, we've never directly studied black holes anywhere near these extremes. PhoenixA may represent one of our first opportunities to test whether the laws of gravity remain unchanged at the most enormous scales nature can create. And then there's time. Human civilization measures history in thousands of years. Stars live for millions or billions. But black holes like PhoenixA operate on timescales that almost erase human perspective. When the light we see from PhoenixA first began its journey toward Earth, our planet had not yet become what it is today. Continents were different. Life itself was still evolving toward forms we would barely recognize. Entire species have appeared and disappeared while that light traveled across intergalactic space. By the time it reached our telescopes, human beings had built cities, invented mathematics, explored the atom, and launched instruments into space capable of detecting it. PhoenixA, meanwhile, simply continued doing what it had always done, feeding, shaping, and enduring. This is perhaps what makes PhoenixA so powerful as a scientific discovery. It doesn't just represent a large black hole. It represents continuity on a scale that challenges the way we think about existence itself. Civilizations rise and fall. Planets form and vanish. Stars ignite and die. But objects like PhoenixA remain, almost indifferent to the passage of time, evolving on scales so vast that our entire species occupies only a brief moment in their history. And perhaps the most important question is still unanswered. If one ultramassive black hole can reach this size, what is the true upper limit? Is PhoenixA near the maximum mass nature allows? Or is it simply one example of a much larger population waiting to be discovered? Future observatories like the James Webb Space Telescope, next-generation X-ray missions, and advanced radio arrays may begin uncovering answers. They may find even older black holes, even larger ones, hidden in the darkness of the early universe. Until then, PhoenixA remains one of the most extreme objects humanity has ever observed, a gravitational giant, a cosmic mystery, and a reminder that no matter how far our knowledge expands, the universe always seems to be bigger, stranger, and far more patient than we are.